So what we're going to go through today is understanding how we generate these random samples based on likelihood functions, blah, 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 blah. So I guess most of you, at least some of you, I should say, have maybe need to be refreshed about what that actually means. So the very first thing we're going to do is go through what we covered in the first webinar and the second webinar to reset the scene. We're not going to go into too great a detail because that's what those first two webinars, but what we do want to do is make sure that we're all ready to understand what the next step in this process is. So when it comes to reliability engineering, we often are faced with reliability data and analytical outputs of software systems or platforms or Weibull plots, and we sometimes don't know what to do with that information. How do we relate that back to a decision maker who needs to make a decision regarding, anything? So in the first webinar of this series, we looked at what we usually come across as reliability engineers. And the first thing we often come across when it comes to data analysis, well, this thing's not working, my little clicker's not working today, is we get data, which is essentially time to failure data. Now, it's not always time to failure data, but when it comes to reliability testing, we often get data which looks like this. Why aren't you working today for me? And the reason why we have data in this context is because we can't measure reliability directly. It's a random process. Failure is a random process, which means our time to failure is based on a ton of different things, including material imperfections, variation in manufacturing, and last but not least, how people use our stuff. Now, once we get our things onto a test bed or out in the field, we'll observe different times to failure for seemingly identical systems or components. And that is because failure is a random process. We have seemingly identical scenarios, but we have different times to failure. Now, we talked about what Weibull probability plotting is. We actually have a separate webinar for this, but just as a refresher, here is an example of a Weibull plot, which has these really weird skewed axes, which help us identify if the data that, our failure process is described by what we call the Weibull distribution. And we know if we plot our data on these particularly skewed axes, which describe the probability of things that have failed or the expected fraction of things that have failed, if we see a straight line, we can be reasonably comfortable that the Weibull distribution is a good candidate for describing the nature of the failure process. And when it comes to answering important questions, what we actually need to do is look at all possible explanations of this data here. And we call this set of possible explanations, at least I called it, the posse of Weibull distributions. Now, this posse is not just a bunch of lines which look good. No, this posse is based on the likelihood of each one of these lines describing the data. So a line which is unlikely to describe the data will not get into our posse. The lines that are more likely to describe our data will get in, and that's what we're going to cover today. And the reason we want to do this is because if we want to, find the reliability or failure probability at 2 years, we simply find where each one of these posse lines crosses 2 years, and on our Weibull axes, we can simply work out where these dots are, and it allows us to understand or create another posse of failure probabilities at 2 years. Now, the problem we were trying to solve from our first webinar was understanding the likely costs and benefits of a warranty period of about 2 years. So we're able to transpose this posse of expected failure probabilities at 2 years and essentially create this lovely histogram which summarizes our uncertainty or all our information about the scenario based on the data we have observed. Now, this is all well and good, but we need to convert this into something that makes sense for our decision maker, which is obviously money. So we can convert failure probability into expected profits per unit. And if we keep going, if we keep having enough samples, we get this lovely line here, which allows us to say things like, hey, we expect there's a 40.73% chance of making a loss, and there's a 32 cent, we expect to make 32 cents per unit profit. Now that's the webinar number one. Now I went over that very quickly by design. I would encourage people joining us for the first time to make sure you go back and look at the first webinar to understand the context of what we're trying to do. The second webinar took it to the next level. The second webinar, we examined what you need to do to create that posse of possible explanations of how our thing fails. And we introduced the concept of the PDF, the probability density function, which is essentially a function which gives us for example, the density of failures we expect to see for a random failure process. So you can see here for this data set, the corresponding PDF curve is highest where our failure points are the most dense and lowest where they're more sparse. So this is a candidate PDF that could describe our data. Now, the way we work out if this PDF is a good candidate or not is if we simply create an expression for what we call the likelihood. And all we do is multiply the PDF values at each data point to create this number here. So on the right-hand side, in the second webinar, we went through and identified the likelihood of this PDF, and you can see quite clearly here on the right-hand side, it's about 14% up our scale of likelihood. Now we can look at different possible PDF curves to identify the likelihood of this curve entering our posse. In this case, there is a roughly 14% chance of this particular curve getting into our posse. Now, if we looked at different candidate PDF curves, clearly this one is unlikely to describe our data. We can calculate the likelihood of this particular PDF curve, and we can see quite clearly this curve virtually has no chance of entering our posse of lines. The most likely curve looks like this. This is the curve which has the maximum likelihood of describing our data by simply taking the product of the curve value at each data point. So using this particular maximum likelihood curve, we're able to estimate the Weibull shape and scale parameters for this particular data point. Now, if we look at a similar bell-shaped curve, the most likely one is 7 times more likely than the other bell-shaped curve you can see here. But how can you as human beings look at these two curves and realize one is more likely than the other? You can't. So that's why we need to calculate what we call the likelihood function. The likelihood function is based on these equations here. So if we have ×2 failure, we're able to use a PDF value. If we have a time where failure occurred before, we're able to use a CDF function. We have a time where failure occurred after, we use a reliability function. And we can use intervals as well to work out the likelihood of a particular thing failing between some initial observation time and a final observation time. So again, very high level, somewhat rushed, but if you are joining us for the first time, please look at our first 2 webinars because that sets a scene for what we're about to go through today, which is how do we create our posse? We looked at the likelihood function of different explanations of our data. How do we actually go through the process of creating a bunch of candidate lines, candidate PDF values, candidate CDF values, CDF functions, I should say, to explain our data and use that list or that set of candidate, our posse, I should say, to help us answer questions like what is the expected profit for our electronic consumer product given the warranty failure probabilities, so on and so forth. Well, how we get our posse is by using this thing called Markov chain Monte Carlo simulation, which is a really intimidating title, but it's quite simple. So if we go back to the problem which started it all, we had a bunch of data points for our product. We need to answer our boss's question, how much money will we make based on selling this product given warranty costs and everything else? Well, we start off with this data here. We use some sort of test, we use some sort of field data, whatever it was. We got these data points, which are times to failure for our product. But this is the data which contains information. It's up to us now to extract the information from these failure points to then work out what the warranty failure probability is going to be. Now, having gone through the second webinar, we talked about the likelihood function, and the likelihood function changes for different combinations of Weibull distribution parameters. Now, the Weibull distribution is made up of 2 parameters, the eta and the beta parameters. So for each combination of eta and beta, we have a different likelihood. And that allows us to create essentially a surface which summarizes that likelihood. And this is what the likelihood function for the data we just looked at looks like. You can see it is clearly a single peak. This is good because that means there's some likely value at the heart of this mountain, which is going to give us a good central indication of the failure probability characteristics of our thing. But we can see that there is some uncertainty involved because failure is a random process. So it's not a single column shooting up at the one and only value. No, you can see there's a bunch of different possible eta beta pairs which have different likelihoods of explaining the data. So again, this is the likelihood function of all data, and we use this likelihood function to get our posse tickets for each candidate combination of the eta and beta to allow them to enter our posse, which we then go on to use to answer our questions. Now, this requires a computer to generate, obviously. I didn't draw this, got a computer to do it. Other thing, so computers are really good at drawing stuff, but they're not good at seeing stuff. So computers can't see this shape. They don't even know what a shape is. So even though we can see this shape and we can tell that there is some central value, we can see that the likely values, the likely eta and beta pairs tend to cluster around a central value. Our computer friends can't see this, but we need our computers to help us go on to the next step, which is to create that representative sample to create our posse of candidate Weibull distributions. So we can see that the highest point, for example, is right here. And that means that if we look at the values for that highest point, or we look at where that highest point occurs, I should say, we have a shape parameter value, a beta parameter value of 1.629, and a scale parameter value of 9.137, which means that if we go back to a Weibull plot, and we plot the CDF curve based on this on these values, we get this line here, and you can see it seems to correlate with the data really well, which is always a good sign. If you do any analysis and you have a maximum likelihood estimate and you plot that curve on your data and it seems to fit well, that's a really good sign that your analysis to date is spot on. So let's go back to our likelihood function. This is what it looks like. Remember this shape. Computers can't see it, we can, but we need computers to help us generate a bunch of samples based on this likelihood function. So how do we get our posse based on this curve, which we can see but computers can't? The most classic approach is what we call the random walk algorithm. And what that means is we tell our computer friends, hey, you start at a particular point and I want you to take random steps. And based on each step you take, I'll tell you if you're heading in the right direction or not. And if you're sort of heading in the right direction, you take that step. If you're not heading in the right direction, you don't take that step. And that leads to this random walk behavior. So you can see here, we have this computer generated random walk, and we're generating all these random data points, so all these eta and beta pairs based on our likelihood function. That's random walking. But obviously we can take different size steps. So for example, if we want to take bigger steps, we can move more quickly over more terrain. So the way we take these steps here is we take a random step in any direction. We then then we randomly select a number between 0 and 1. We calculate the likelihood function at our new candidate point, We divide that likelihood by the likelihood at our first step off point. And if that ratio is greater than our random number we selected in the step, 3 steps ago, we can finish that step. And otherwise, we stay put. That's how our random walk happens. So if we want to take bigger steps, obviously you can see it's the same random walk behavior, but we're moving more quickly across the candidate space. Now this looks like there's a lot fewer points, but that's not the case because in this case we're taking big steps where it just so happens that we're less likely to move off the place we're currently standing. which means we have lots of points with identical values, which is not the best. So this is a different random walk approach where we're taking bigger steps. Conversely, if we take steps that are too small, we never get to explore the entire random space. So here we started off in exactly the same place, but our step size is way too small. We just barely even reach the foothills of our likelihood mountain. So we never get to truly explore it. So these are some of the issues with this random walk approach. Very a popular approach, but you have to really know how long those steps need to be or how far those steps need to go. So let's go back to sort of the middle ground steps. We start off down here. We're going to do a lot more sampling in this case, a lot more walking, and you can see that over time we will finish out. We will keep doing this random walk behavior, hopefully across as much of our likelihood surface, our likelihood mountain as possible. And when we do that, we're able to look at those data points and say, you know what, we can clearly see some characteristics here. Now you can see that in this case, we do tend to have our random points, our posse clustered around our likelihood mountain, but there are some problems. Our first little meander where we started down the bottom left-hand side, we obviously have some data points which aren't representative. That was just us trying to get towards our mountain of likelihood. So we need to really exclude those data points. And you can see that there's some spaces on our curve, on our hill, which aren't really covered. So we need to get the right step size to try and make sure we cover our mountain of likelihood accordingly. So this is what we call a random walk algorithm, and I hate it because there's so much fine tuning you need to do. There's so much help you need to give your computer to do this random walking stuff. You need to go in and make sure that there are things happening like what we call converging criteria, where we make sure that the data points are an adequate representation of the thing we're trying to model. It's so finicky. It is very useful in terms of minimizing computational power, but there's so much fine tuning you need to apply that I try to steer away from it. And it's particularly, that's something we can do in reliability engineering, where realistically these sorts of problems are quite simple in the world of probability and statistics. So is there another way? And the answer is absolutely. There is another way, and this is the way I use, or this is a model close to the way I use it. So before I talk about another way of trying to create our posse of candidate Weibull distributions, I need to do something first. I need to introduce the concept of the rectangle of death. Now, the rectangle of death is an overly dramatic term, and hopefully I reinvigorated your attention for this webinar, because I actually intended to say the rectangle of guess, which is a lot less intimidating, but hopefully some of the fear and awe that you got just from hearing the phrase the rectangle of death is going to carry over into what I'm about to talk about, because I want you to remember the rectangle of guess through the subsequent slides, through the subsequent animations, so you really understand the main points of what I'm trying to say. Okay. Before I go on, I'm going to open the floor to any questions. Are there any questions on the random walking algorithms we looked at so far? Any questions at all? Okay, I can't see anything coming through, which must mean I'm nailing this webinar. Probably verbose, but we'll see how we go. All right, so the rectangle of guess. We looked at a random walk algorithm, and remember, that algorithm is intended to create a set of Weibull distribution curves which describe, which become our posse, and that posse is then used to help us answer really useful business questions. Again, the challenge we're trying to solve is bridging the gap between reliability analysis and helping a decision maker or boss or director or CEO make a decision, and do that in a way where they actually like us as reliability engineers because we helped them and didn't get in the way. So the rectangle of guess. Let's go back to our likelihood function based on the data we observed during our test. Remember, computers, they cannot see this curve or this surface. They can't see it. We can if we know what we're looking for, but we're asking computers to do this for us. So the approach I'm going to advocate goes a little bit like this. We start with the random point. So let's just say we take this random point here. And it has some height, so the likelihood is relatively high. It's about, say, half the highest point, half the height of the highest point of our likelihood surface. But that doesn't matter too much. We have randomly selected a point. In this case, this point has a beta value of 1.4 and an eta value of 8. And you can see that when we have this little cutaway, it gives you an idea of where this point occurs in our likelihood surface. So the next thing I want to do, once I've got this random point selected, is then work out its likelihood, which should be pretty easy to do. If you followed what I did for the second webinar, we showed you how to calculate the likelihood function. We calculate the likelihood of a beta parameter being 1.4 and a shape parameter being of 0.8, explaining the data we see. Once we have this height, this likelihood height of our randomly selected point, we then randomly pick a value within this height. What that means is we uniformly randomly select a point. So in this case, when I randomly selected a point within the height of this particular surface, it turned out to be shown, you can see that red line there, that horizontal red line, that represents that randomly selected height. And when we go back to our surface, the next thing we do is cut it off. So we essentially create what we call a slice through our surface at this randomly selected likelihood height. This becomes central to everything else we're about to do. So the slice, in fact, this approach is called slice sampling based on this particular this particular characteristic or this particular step. So once we have a slice, we then randomly select a data point within that slice. Now that's all well and good, but remember, computers can't see the shape. That also means computers can't see the boundary of our slice for the selected height, which is a problem. So what we can do is create a rectangle around our slice, and in that rectangle, our computers are able to then generate random values. But we need to make sure that our rectangle contains our slice. So we typically like making sure that our rectangles are big. We want to make sure we have a really good chance of our slice appearing within our rectangle. We want to avoid this sort of stuff where our rectangle is either only partly covering our slice or missing our slice entirely. This is what we call the rectangle of guess. Our computers can deal with our rectangles of guess. What they can't deal with is visualizing the shape of our likelihood. And once we have our rectangle of guess, our computers can then start randomly picking points within this rectangle. And they'll keep going, and they'll keep going until, huzzah, we have a randomly selected point that occurs within our slice. And once that happens, we stop. This new point, this new beta eta pair becomes, it now gains access to our posse of Weibull distributions. So you can see straight away that if we increase the size of our rectangle of guess, we are less likely to miss our slice. But we make our algorithm less efficient. We need to have lots of misses, so to speak, before we finally get our point that occurs within the slice. So this is something to be aware of. There's lots of criticisms of this approach, But with today's computational power and with some of the realities of reliability engineering and the data analysis that you tend to go through when you have times to failure, they aren't as relevant anymore. We can make our rectangles of guess really, really big. It will take a little bit longer for our computers to go through this process, but to an extent, even with just basic laptops today, it's still not that long. And when I do this, I actually have a slightly modified approach where my rectangle of guess is a little bit more fine-tuned. That's something I'll talk about next week. But at the end of the day, for this particular approach to creating our posse of viable distribution values, viable distribution parameter pairs, this is a really useful way of creating that posse. So once we have our once we randomly selected a point within our slice, that becomes the starting point for the next step of this process, which is repeating what we've just done. And when we do that, this is what we get. Here are about 1,000 data points being randomly sampled from our likelihood surface using that slice sampling approach. And once we go through these steps, and when obviously we can keep going if you want to increase the accuracy, we can have hundreds of thousands, millions of points. This animation was relatively slow. It was slowed down so you can see these points being created. But with computers today, they are creating these points so fast, it really doesn't matter. So if we look at these data points on our axes again, the first thing you should see is that using the eye test, it seems like these data points genuinely do seem to reflect the likelihood surface based on our data. It seems to be a pretty good representation. I'd hope you'd agree. Now, if we compare that to our random walking algorithm, you can see that there is a big difference. On the Metropolis Hastings algorithm, which is that classic random walking approach, you can see that the data points within the surface itself, they appear to be clustered around certain areas. And that's because we need to keep fine tuning. We need to get the step size right. It just so happens that the most efficient step you take, the most efficient step duration is roughly the standard deviation of that surface itself, the likelihood surface that we can't see. So that's all well and good, but if you don't know, if your computer doesn't know anything about the likelihood surface itself, then you're not going to have what we call early convergence. You need to do tons and tons of samples to make sure that you're comfortable that your random walk has happened to walk all the way around your likelihood mountain. And of course, you got that burn-in stuff as well, that little trail in the bottom left-hand corner. We need to get rid of that. So I always use this slice sampling approach with a little twist that I'll be covering next month, I should say, not next week, to make sure that we have a much better, much more representative set of, in this case, eta and beta pairs to help us answer those questions. So before I go on, are there any questions? I see there's a couple of, sorry, I'm just trying to expand my question box. I believe I can. Why can't I see these? I might have to pop you out questions. There we go. So the question from Shribetson is, what is the beta and eta corresponding to the apex of the cone? Good question. So I'm going to go back to the slide where we actually showed the apex of the cone. Shribetson, have you ever heard of the maximum likelihood estimate? Yes. So I know it's a little bit hokey using the comments page, but are you able to give to me in your own words what the maximum likelihood estimate means to you? Just waiting for that response to come in. Obviously, a few words need to be communicated. So while Stribertson's crafting a response, you'll see up on the screen right now, we go on back to that slide where we looked at the location of the apex. So yes, you're 100% right, Stribertson. It is the apex point. This is the maximum likelihood estimate. But what does a maximum likelihood estimate mean in terms of the statistics, the probability, the interpretation of the data? What does maximum likelihood mean for the Weibull distribution that these two numbers define? Just waiting for the response to come through. Technology, it's all good. What does maximum likelihood mean? So while that's happening, okay, I understand. So for those who can't read the comments, poor old Stribertson only has a mobile phone, so his thumbs aren't that lubricated to be able to keep up with what we're talking about. So let's keep going about what maximum likelihood means. We often hear this term in reliability engineering called the maximum likelihood estimate. So remember, in this case, based on the data we had, you can see the apex of this likelihood function, which corresponds with the maximum likelihood. That's exactly what it means. It implies a beta parameter of 1.629 and a scale parameter or eta of 9.137. So what if we were to plot the Weibull distribution CDF over our data, we get this red line here. That red line, hopefully you can agree, seems to be a pretty good line of best fit candidate, and that's exactly what it is. This is the line which is the line that is most likely to explain the data we have observed. It is not the only possible way of explaining the data we have just seen, but it is the most likely curve. And what does that mean? Well, we go back even further and we go back to what we covered in the second webinar. Here is a candidate PDF curve for this set of data. You can see perhaps it looks like a good fit. If we take the height of that PDF curve for each data point and multiply it together, we get a quantifiable estimate of likelihood. In this case, the likelihood of this particular PDF curve describing the data is shown on the right-hand side with that particular with that scale, that continuum. So in this case, this helps us work out the likelihood of this particular PDF curve getting into our posse. Now we compare that likelihood to the likelihood of this curve, which you can see clearly doesn't marry up with our data points. And the likelihood function, the product of all our PDF curve values at each data point, bear that out. Our likelihood on the right-hand side is at the very, very bottom of our scale. And remember, the likelihood of a candidate PDF is a product of these values. The maximum likelihood estimate, all right, is this curve here. This is the Weibull PDF, which if we go through all candidate PDFs, has the maximum likelihood. This is the most likely PDF curve that describes the data we are seeing. It is more likely, obviously, than this curve here for obvious reasons. You can just see this curve here does not visually pass the eye test in terms of marrying up with our data. This one does. and we've gone through the steps of asking your computer to work out which curve has the maximum likelihood, which is this curve right here. Now compare this to our first curve we looked at, which looks similar in shape, but is 7 times less likely. So even shapes which look somewhat similar to us humans have a slight change in shape, and they are all of a sudden 7 times less likely. So the likelihood function quantifies the likelihood of a candidate model describing the evidence or the data we see. So the maximum likelihood estimate gives us the Weibull distribution that is the most likely to describe the data we have observed through that random process. Shriverton, is that any closer to answering your question about what maximum likelihood means? Awesome. Are there any more questions before we move away from the slice sampling explanation I just went through? I'd also open it to comments. I dare say at least some of you guys and girls have used Markov chain Monte Carlo simulation, perhaps Metropolis Hastings algorithms, slice sampling algorithms. There's a few others as well, Gibbs sampling. What other approaches have you guys used, if any, out there that might help everyone understand or give context to the stuff we're talking about today? And I appreciate there's a chance that not anyone has done this as well. Just wait another couple of seconds to see if there's any responses. So Mark's only used Metropolis Hastings. Metropolis Hastings is one of the more, I suppose, default algorithms, but it has, yep, those problems we talked about. One of the reasons Metropolis Hastings is the default one in many cases is because if you do go through that fine-tuning process, it tends to be somewhat efficient in terms of rapidly generating these sample points within reasonable periods of calendar time. But again, you have to know what you're doing with the fine-tuning stuff. You have to know what you need to do to get that right, what we call proposal density, which tells you how far each step is going. And once you do that, then yes, you do have some assurances that you will have a representative sample. The reason why Metropolis Hastings is really popular is because of that efficiency. When computers were a lot slower than they are now, this random walk algorithm took a lot of time. And don't forget, it was built for lots of other problems which have more than 2 parameters. So we're just looking at a random walk over a hill. Imagine not just a 2-dimensional surface, a 3-dimensional surface or a 4-dimensional surface. Sometimes we need to, in the world of physics, need to solve problems which have maybe 6 to 8 parameters. So it can get somewhat complex and complicated. And now in the past, when we've had slower computers, the efficiency of Metropolis Hastings has been a really useful benefit of that approach. So slice sampling is not nearly as efficient in that context, but we're often only dealing with 2, perhaps 3 parameters. And with computational power, the inefficiencies are really not that big a deal these days. And the benefits of slice sampling and approaches similar to slice sampling are that you get a much better representative sample. You don't need to do nearly as much fine tuning. All you need to do is to make sure that your rectangle of guess is big enough to contain your slices. And we're going to go through how we make that happen next week. So that's what Markov chain Monte Carlo simulation is all about. Here are 2 examples of it. We are trying to get samples that represent, we're trying to select samples whose likelihood of acceptance into our posse of samples is based on the height of our likelihood surface at those points. So we've gone through that process. you might recall during my first webinar, I put some code up on the screen, which generated these points. It used a function called slice sample. So that couple of lines of code was all we needed to create these samples here. Now, this is just 960 samples in this case, but realistically, there's no reason why you can't go up to hundreds of thousands, just to be doubly sure that you are going to have a really, really good set of representative samples. So once we have our set of samples, again, I'm advocating for slice sampling, but you can use whatever approach you want as long as you know what you're doing. We then use those samples to answer questions. So let's go back to our Weibull probability plotting paper. Here are the data points from our test of our consumer product. You can see on here we have that red line, which represents Srivatson's maximum likelihood estimate of our beta and eta parameter pair. Our beta parameter, that's our maximum likelihood estimate for our beta parameter, was about 1.6. Our maximum likelihood estimate for our scale parameter, eta, was about 9 years. And when we plug those into our Weibull distribution and plot the CDF curve, this is what we get. So it's really good validation of our underlying analysis. But then we use slice sampling because we can't base important business decisions off a single line of best fit. That's silly. It doesn't incorporate the uncertainties. We need to incorporate that uncertainty because failure is a random process, and we use our posse of candidate Weibull distribution to do that. So we've just done slice sampling, and here are some lines based on the first X number of slice sample pairs. I haven't put them all in here because it would simply turn into a red bar. So I just want you to see how we have some sort of clustering effect based on our clustering effect where these lines tend to not deviate too far away from our maximum likelihood estimate. And for each one of these lines here, we're able to calculate, obviously, the failure probability at 2 years. It's quite simply where these lines intersect with our 2 year mark, at our 2 year mark. And once we do that, we now have a posse of reliability estimates or failure probability estimates at 2 years. And we can plot that posse in a histogram. That histogram we can then take away from this now messy Weibull probability plotting paper, because we don't want our boss to see this necessarily. That's going to do more to confuse instead of aid. And we take that histogram and start making it more user-friendly. So here is our histogram of warranty period failure probabilities based on our posse of candidate Weibull distributions. We'll see a comment coming through from Paul saying it looks like the slide hasn't updated on your end. Could I just ask a general shout out? Is anybody else able to see updated slides just to confirm if it's a local issue or a general issue? So there's no updating. Slides are not updating. Interesting. Let me see if I can. I'm going to try. Can I get an can I ask people? You got it now? All right. I'm going to advance one slide. Let's see if you can see. Can anyone confirm if that has now moved to a simple histogram? Okay, so let's, oh good. So I'm not sure what happened there, but let's just go, just to make sure I covered everything. This is our data, this is our Weibull probability plot. Our red line here represents our line of best fit. Our line of best fit isn't going to give us anything meaningful in terms of risk-based decision making. We've just gone through slice sampling. Here are the first number of samples plotted on our Weibull probability plotting paper. Remember, each sample contains a beta and eta pair of parameters, and each of those pairs define a single line. This is our posse. Now, because we've got a posse of lines, we can also create a posse of failure probability estimates at 2 years. is simply where those lines cross our 2-year line mark. And once we've got that posse, we are able to create this histogram here. But I think I'm not sure where we left off in terms of slides not updating, but we don't typically want this particular image to be put in front of our decision maker. It's too confusing, it's not initially useful, and it will take too long to explain what is going on here. So let's simplify it. Let's take this histogram out of there, and let's simply create a histogram based on probability of warranty period failure. So this histogram is not a histogram of test results per se. This histogram represents our uncertainty in our warranty period failure probability. So we can see that our uncertainty isn't complete. We do have some idea about where our likely failure probability is going to occur, but we can also communicate, at least graphically, how our uncertainty propagates throughout this estimate. But warranty failure probability is not of itself a useful metric when you're making a decision. It's very, very important, but reliability metrics by themselves or in isolation are somewhat useless if we don't embed them in the business context. Now, in the first webinar, we talked about how we convert failure probability estimates into expected profits for each thing we sell. And so when we take that into consideration, we can see here is our histogram of expected profit per unit. And if we keep doing slice sampling, so we have so many samples, eventually we can replace our histogram with a single smooth line. And this smooth line in this scenario tells us, or is able to say to our boss, hey, as it stands, if we launch this product, there's a 40.73% chance, based on our understanding of reliability, that we will see a loss based on because the extent of warranty repairs will obviously overwhelm our profit margins. We expect that on average, we are going to make a 32-cent profit per unit. So that's why we went through that whole process of slice sampling, to get that posse to help us answer questions like this. So what is next? What we're going to talk about next month? Well, the reason I talked about, went through what we did today, was to make sure that people understand what is happening when we do this thing called Markov chain Monte Carlo simulation, specifically slice sampling. Here is a snapshot of the code I used in the very first lesson. Now, there are a couple of issues with this code. There are things that you would never do in real life with this code as you see it. Now, I'm not trying to be dramatic, but this is in many ways an unstable command line, or an unstable call for a function in this case MATLAB, because of things that we're going to go through next month. So next month, we're going to go through how we create not only this particular code, but better code for your scenario, for your application, where you're almost certainly going to guarantee a good outcome, a good answer. We're going to go through the actual keystrokes to making this happen. So what we need to do is remember what we went through today. Remember the rectangle of guess, because that rectangle of guess is something you can influence when you're doing, in this case, slice sampling. And you have to influence it. If you don't influence it, there's a really good chance you're going to get a bad answer, and we don't want to do that. Just to recap, I don't like Metropolis Hastings for reliability applications, because the benefits of its so-called efficiency are outweighed by the intricacies of all the fine-tuning stuff, and our computers today can really deal with a lot less computationally efficient algorithms like slice sampling, but we get a much better answer as a result. So we now need to generate code that works. And that little snapshot there of code that I use to generate this, these are sets of this posse. We're going to go through why that is not as good as it could be, understand some of the key inputs to making it more robust, so that when you go back to the big wide world, you're able to answer these questions with a high degree of confidence. So I've got about 10 minutes to go, but are there any questions about what we've covered today? understanding that I didn't dwell on webinars 1 and 2 in any great detail, because the intent is, sorry, the requirement is for you to understand that content. Go back to webinar number 1, go back to webinar number 2 and review that if you haven't already. If you've done that and you've still got questions, please feel free to start asking them now. Is there anything we want to go over again? Again, feel free to let me know. Okay. Not a lot coming through. It can't have been that awesome. Surely there's something I went through too quickly or didn't explain as well as I could have. For next month, are you going to cover the code using MATLAB and R? And the answer is yes. Now, thanks, Mark. That's not a question, but I'll take it. With next month, we're going to do both MATLAB and R. Now, R is obviously preferred by a lot more organizations. The thing about MATLAB, though, is it does have some more existing functionality as well, and it allows you to do a lot more pretty outputs as well. But yes, we'll do both R and MATLAB. I'll be interested to see beyond this. I think next week will probably be the last one. Last one in this series of webinars. When I first did this, it was going to be just the one, but we've had some crazy requests thereafter to keep going. But I'll be interested to see if there's any appetite for this to be made into more of a formal course, because if you know how to do this and you do it well, in some cases you can even do it in Excel, you can get a better outcome than using off-the-shelf software. Now, off-the-shelf software, if you looked at what we did in webinar number 1, we just showed how inaccurate that can be, because they don't use Markov chain Monte Carlo simulation. They use algorithms that make their life easier, but not yours. And those algorithms also don't give you these wonderful samples that you can then use to create your own risk-based decision-making profiles for bosses, such as, what's my expected profit? So I'd be interested to see if there's any appetite for us to actually formalize what we're talking about, and to make it maybe a bit of a course where we can make sure that you're able to do this in a more certifiable way, I should say. Okay, how is this posse different from the contour plot generated in Weibull++? Now, the contour plot itself is essentially a different way of visualizing the surface, the likelihood surface. So let's go back to our, let's go back, let's say here. So there is our surface. Now, the contour plot is simply another way of visualizing that likelihood surface. Now, if I was to look at it from above, I could replace the colors, the gradients with contour lines to give you essentially the same thing that that Weibull++ does. The thing is that when Weibull++ and virtually every other off-the-shelf product that claims to do this, what they do, and this is probably a good visual to show you how they do it, is maybe I'll remember that for next time, is they replace this particular surface with a three-dimensional or two-dimensional bell curve, I should say. Three-dimensional, or either way, a surface based on a bell curve, because that then makes the computations easy after that. So they find an approximate fit for this particular likelihood function. And when they do that, they introduce a ton of uncertainties, especially if you don't have a lot of data. So if we look at this one, you can see as we rotate that this surface, it's not symmetrical. It's got some weird shapes going on. It's not a bell curve shape. It's just not. You can see there are some bell-shaped profiles, but it has almost a triangular, or it's almost like a pyramid in a way. So if we go to the next one, you can just see how extensive this is. That's not a smooth circular bell-shaped mountain. Now, even though Weibull++ can reproduce the contour lines which show this mountain, when it comes to actually solving problems, they replace it with an approximation. And that's where we get the uncertainties. Can you give some pointers on how to do this in Python next month as well? Okay, I'll see what I can do. Obviously, we're up to three languages, three coding languages now. I'll never say never, but by the same token, we all want to balance this free webinars with sleep time as well. But I'll see what I can do. If your slice height of likelihood a minimum you select for useful data, is your slice? I don't think I understand the question. If your slice height of likelihood a minimum you select for useful data, I'm not entirely sure what you mean by that. I might be introducing confusion by saying we randomly select. The computer randomly selects a height value for us. So we don't have any pointers. We don't, as humans, don't provide any inputs to the computer selecting that random height value based on our slice or to create a slice. That's a part of the algorithm is to make sure that that is randomly selected by the computer. I'm not sure that answers your question, but we don't have to provide any indications about the height of the likelihood function for our slice sampling algorithm. Does that answer your question, Mark? Cool. So again, if you can master this, then you have not only saved your organization how many tens of thousands of dollars of licensing fees to use Weibull probability plotting software, but you're actually able to take this information and transplant it into your own decision, which is a huge key, a huge benefit. It's all well and good having these lovely confidence intervals up on a screen, but how do you use those confidence intervals to create or answer your question, answer the question of your boss when he or she is asking you, what is the likelihood of me making a profit for this current product, for example? So you can't, if you know what you're doing, you are able to take everything we just talked about and create this curve here. Whereas if you use an off-the-shelf software, beyond the inaccuracies of the assumptions they make, you can't at least easily extract the information you need to create this really cool curve. At best, you can take confidence bounds out, but those confidence bounds will give you essentially a left and a right of arc on this line here. It's very difficult for you to get an expected value or anything that your boss would really want to see. So if you're able to master this stuff, you become a better reliability engineer. You spend a lot less on licensing software, licensing fees for software, and you're able to make your boss happier all the time. Any more questions? Any relationship between the confidence bounds and the posse? Yes, absolutely there is. So Srivatsan, if I was to go back to, if you do want to create confidence bounds, no, they're not the same. So here is if you look at this slide now, you can see there's a bunch of lines on the screen which are representations of individual posse members. Now I can use these these posse members to create upper and lower confidence bounds. And how I do that? Well, for example, if I go to 2 years, I can create my posse of failure probabilities at 2 years, and there's my histogram. Now from that histogram, I can simply find the 10th and 90th percentile, for example, to create an 80% confidence bound at 2 years. Now, again, the computer can do this a lot faster than we can, but for every time period on the x-axis, we simply create our posse of failure probabilities, work out the 10th and 90th percentiles, and that will give us our 80% confidence bound, which we can then plot on top of this. In fact, I'll probably do that in the next generation of this presentation. But again, we did cover that in the first webinar as well. So we can use our posse to create confidence bounds. But again, our posse is so much more powerful than the confidence bounds themselves. Our posse has a ton more information. So imagine going from that, and instead of getting this here, you might be able to say, hey, look, I am 95% confident that we're going to have a profit per unit between -$5 and $7, plus $7. That's great. That could be useful, but it's not nearly as useful as this. Now, I can use this to create confidence bounds as well if my boss needs it. So once you have this curve, you're able to answer virtually every possible question your boss is going to ask you about how the reliability of your thing is going to affect the bottom line. It's much more useful, much more robust as well. So if we have the posse, can we dump the confidence bounds, so to say? Yes, we can. I do think it's also quite useful to represent uncertainty. So how you're going to represent uncertainty is important. So your boss might be really comfortable with confidence bounds. So you might want to have confidence bounds in any chart you give them. So this particular histogram here represents the uncertainty in our understanding of profit per unit. If you want to dump the posse per se or use the posse, then that's all well and good, but you still need to have some way of communicating uncertainty. This is the best way. You can just choose to communicate uncertainty with whatever metrics matter the most. So yes, you can dump the confidence bounds and use this risk-based decision-making profile. It's essentially up to whatever your boss is most comfortable with. Ideally, your boss would learn to embrace risk and be comfortable with making risk-based decisions, which means they'd want to see this curve and not just simply upper and lower confidence bound estimates. We do need to cater to the maturity of our boss or decision maker when it comes to risk-based decision making as well. Cool. Any more questions? No worries, thank you, Srivatsan. Don't forget, we've got some handouts as well. Should be available. So let me know if there's if you have it. And again, during the next week or next arbitrary period of time, feel free to reach out. My contact details are on Ascendo. Thank you for that, Jeff. Looking forward to seeing you guys virtually next time as well. If you do have any suggestions, questions, queries, I also, again, want to improve this as we go over time. If there's any any appetite for this being turned into maybe a more formal approach, a formal course where we can really dial in your skills, let me know. We'll see how we go. Thank you, David. Michael, thank you. Pradeep, same to you.